Hello and welcome to the course of digital image processing using Python. I am Ahmed and we will be discussing Canny Detector. So one slide for revision. This is the last topic we discussed. Gradient. So gradient is a little bit different from all the operations we did throughout in this course, like point pixel operation or mask operation. So in case of point pixel operation or mask operation, I mean the smoothing and the Laplacian like. So in all cases we used one image as input and we produced one image as output. But in case of gradient, we take one image and we produce two images. So first we compute gradient along x-axis and then gradient along y-axis. Then using ix and iy, we compute magnitude and the orientation, r, angle, r, direction. So here is the input image. That's the magnitude of the gradient of this image, and then that's the direction or orientation. So here orientations are in fact displayed as color coded, not grayscale. So just to show you the 0 to 360 gradients, all possible angles. Whereas if we encode this gradient orientation image using grayscales like black and white, then definitely either 0 angle or 360 angle will be in fact merged with the background, the black color. So it's better to represent this gradient orientation using color, different colors like spectrum like colors. So one thing is important: when we compute ix and iy, there could be values like positive and negative values. So we usually typecast this image from uint 8. I mean this image is originally an 8-bit image, and then we computed ix, which is the gradient along x-axis, and then iy, which is the gradient along y-axis. So we in fact typecasted this image to float type. Then we compute ix, then iy, then we computed the magnitude, and similarly this orientation matrix. So initially these magnitude and orientation matrices are images are in float type. So it's up to the programmer how we convert this to displayable images. The simplest way is to convert this image to 8-bit, this floating point image to 8-bit image. This way we will get total 256 possible gradient magnitude, and similarly this to 8-bit gradient image, and similarly we will get like 256 different directions, because to display an image you have to convert it to a standard 8-bit format so that the graphics driver can display the image. But mostly we do not require these much gradient magnitude and these much gradient angles. So the best way it could be like if we have, in case of our these operators, we just need, for this pixel we need just only 8 directions like 90 degree, 45 degree, and then 0 degree, and then say minus 45 degree, and then minus 90 degree, minus 135 degree, plus 135 degree, and 80 degree. So we totally need 8 directions. So it's purely an option that if we rather we save this image as 8-bit image or just 3-bit. 3 bit to represent total 8 possible angles. Or we can even quantize it when we are processing it. We can save it as an 8-bit image, but while processing we can process it like possible 8 options, just quantizing to nearest angles 0, 45, 90, like that. Canny edge detector. So Canny edge detector was first suggested by J. Canny and in 1986, and still it is like a standard because of its performance, its robustness, still used in widely used in computer vision and all the advanced applications like machine learning. So the theoretical model is in fact just to detect step edges which are corrupted or contaminated by additive Gaussian noise. So just like this, as we discussed earlier, that edges are more prominent and the noise usually resides on the floors like surfaces, plane surfaces, but edges are sharper as compared to this noise. So and this is a perfect example of a noisy edge. But we do not use simple Laplacian or derivative like operators on these edges, because derivatives in fact enhances the noise. So it's better to first smooth them and then use derivative like gradient derivative like operators. So there are 4 steps just to implement Canny edge detector. First is the suppress noise, as we usually do using Gaussian like filter, and then is compute gradient, magnitude and direction. So we have to retain both the masses, both the computations like magnitude and direction. Apply non-maximum suppression. It's an algorithm that in fact suppresses responses which are clutterous, and just to refine the boundaries. So we use magnitude and direction to apply non-maximum suppression, and then use hysteresis, which is a threshold like algorithm, and then connectivity analysis to detect edges. So these are the 4 steps in fact. So noise, suppress noise is just like applying gradient, then applying Gaussian and then gradient. So we have already covered these 2 steps. Just we have to study these 2 more algorithms, how we refine the edges and make them more clear boundaries. So here's the example image. We will be discussing the same image for rest of this lecture. So this is the Laplacian of Gaussian, or derivative of Gaussian along x-axis, and this is the derivative of Gaussian along y-axis. And we have almost more or less the same Sobel operator, which is called Sobel operator, in fact 1, 2, 1, which is in fact averaging mask, and then 1, 0, minus 1, or 2, 0, minus 2, and 1, 0, minus 1 are the derivative or differencing operators. So along x-axis it's averaging, and along y-axis it's differencing. So you can see it's a image representation of the same derivative of Gaussian along y-axis, and it's the image representation of same derivative of Gaussian along x-axis. So these are the masks, equivalent masks. These are just pictorial descriptions of Sobel operator, say Sobel operator. So we can say derivative of Gaussian filter. So derivative of Gaussian along x-axis, along y-axis, and that's the magnitude. We have already discussed this concept in our last lecture. We are just going to develop the same concept just to discuss our next two algorithms for Canny edge detector. So orientation of our orientation array, our orientation matrix of the same image. Here we have in fact displayed the orientations as colored image. So orientation is in fact a tan inverse of gradient along y-axis divided by gradient along x-axis. So it would be like a number at each pixel. So we have plotted or shown that pixels as color coded pixels. So these are the directions of the gradient. So let's zoom in this selected portion, and we got this. So apparently in the image the edge is very sharp. It's like looking like some pixel line of pixels, but practically this edge is not that sharp. So that's like a line consisting of wider range of pixels. I mean like 3 to 4 pixel in width, like this width of this edge. So it's important to have very finer, thinner line of edges. So we will apply some algorithms to make these edges more prominent, like brighter white line, a line of pixels, like our line of pixels over here. So the algorithm must be very robust and efficient so that it can preserve these lighter pixels even. So that's the problem of Canny edge detector. So we are done with first two steps like noise suppression and then gradient computation, magnitude and direction. Let us discuss this applied non-maximum suppression. Assures minimal response. So what is non-maxima suppression? Simply it's like dropping the pixel which are in fact lesser in magnitude. So we know that that the gradient reaches maximum and or have maximum value when there is a sharp edge, very sharp edge, and the gradient is very perpendicular to that edge, the direction of that edge, like at the 90-degree of that edge. So that's our previous learning about edges. So non-maximum suppression is simply drop the values which are less than some threshold. I mean smaller values. It means there is no sharp edge there. And similarly in case of direction, suppress all pixels in each direction which are not maxima. Do this in each marked pixel neighborhood. So we can select only 8 angles because in practical image processing it's not possible to have real angles or real valued angles 0 to 360. So we have a pixel and we have 8 neighboring pixels. So there could be only 8 direction towards each neighboring pixel in fact. So here is an example. We have say set of 4 by 4 pixels, and we are centered right now at point Q, and this is the direction of the gradient at pixel Q, and this is the magnitude as well, magnitude and direction. So this magnitude could be like a lesser value. So see if the gradient is displayed like this one, it means it has same direction but lesser value. So right now we have this magnitude and this direction. So we do not have any pixel in this direction right now. So we can interpolate these two values like an average of these two pixels, and we can calculate a value over here virtually, not practically because there is no memory location in that array. And similarly, if the direction is this one, then we can compute an interpolation of these two pixels over here. So we have to simply compare the value over here and the value over here. If this value is smaller than this, it means that this is a stronger edge, or this point is representing a stronger edge. So we have to leave it as it is. So if this value is smaller than this value, then we have to place a 0 over here. It's like suppressing the non-maxima. So if the pixel under consideration is lesser than the pixel or virtual pixel, which is in fact an interpolated value of this pixel and this pixel, if this value is lesser than this value, so we calculated this value just be based on the direction and the magnitude of the gradient. So if this value is smaller than this value, then we have to place a 0 over here. That's like suppressing the non-maxima gradient. So edge is more sharper over here and less sharper. Just like consider this one. You will get a smaller value over here. So we will get a smaller values over here of the gradient, definitely in this direction, and we will get maximum values in the center. And that's how we in fact thin this border to get more sharper boundaries. Here's the output. That's the this image is displayed before thinning or non-maximum suppression, and this image is displayed after non-maximum suppression. So there are more finer and thinner boundaries as compared to this one, and you can see there are more shades, like from white to black, as compared to this one, this image, which is the output after non-maximum suppression. So the last point is use hysteresis and connectivity analysis to detect edges. So this image is produced using simply thresholding. You can see there are some gray levels like this over here, over here. So these gray levels are in fact dropped. So once again, linking edge points. Consider this mark point as an edge point, and this time you have to move along the 90 degree of the gradient. Say we have gradient along this direction, and this is the normal direction to the gradient at 90 degree. So you have to search the connectivity along this direction, because if this is the edge, then gradient will definitely point towards the direction of maximum change. But the connectivity for edges, you have to find connectivity along this direction, whether this point is an isolated point or it's a connected point. So you can make like 8 connectivity or 4 connectivity algorithms just to check whether this point is connected or not. So edge hysteresis, it's all about thresholding. So the idea is to define two main thresholds, like k high and k low. I mean the value of the magnitude of the gradient. So you can define two thresholds like k high and k low, and so roughly the ratio between the low and high could either be equal to 2 or 3. Like that's not a standard value, it's just an empirical value. So you can set the ratio between the two equal to 2. So you can categorize your edges, like if the value is low, less than low, then it's not an edge. If it's greater than high, then it's a strong edge, and it between low and high, it's a weak edge. So we can tag all the edges. So we can make a simple decision based on our tagging, like if it's a high value and we can declare it as a strong edge, and if it's a less than a low value, then we can drop that pixel. But if it's between low and high, then we can check its connectivity with other pixel in all directions. Like if it's connected with a strong pixel, then we can retain that value which is in between low and high threshold. So that's called hysteresis thresholding. So here is the best example. Like we have strong edges and then we have weak edges but connected to edge pixel. So that's why these values are retained in hysteresis thresholding. And similarly, we have some weak edges but connected to the strong edges. Here is the final output of the final Canny edge detector. So this is the original image and that's the edge detector. You can see the edges are very fine, thin, one line of pixels like that. But still there are some issues, like you can see the edge over here is not detected because it's faded. There is a less contrast between the background and the object, like teeth of this alligator. So this edge is not properly captured, whereas where there is a contrast, the edge is perfectly captured as one thin line of pixels. So just a revision of complete Canny edge detector. First you have to filter the image with x and y direction derivatives of Gaussian. So perfectly we have the Sobel operator, Sobel along x-axis and Sobel along y-axis. Then find the magnitude and orientation of gradient. So that would be like two different images or two different masses. Then non-maxima suppression, that is like dropping the values which are lesser than some threshold or in comparison with the neighboring pixels. So we can make an idea using direction of gradient, that where the gradient is pointing, and then in that direction if the value of magnitude of gradient is lesser than the pixel under consideration, then we can skip that pixel. Otherwise we have to place 0 over there. If the value under consideration is smaller than the value in the neighboring pixels, then we can drop that value. So we retain that value if value is greater than the neighboring pixels. So that's non-maxima suppression. And then thresholding and linking, it's about like if we have a pixel and we can categorize that pixel into either an isolated pixel, isolated edge, or some connected edge. So in that case we have to move along the normal of the gradient direction. So in both of the algorithms, in these two algorithms, we need magnitude and gradient, magnitude and orientation as well. So in this way we find the direction and we look in that direction whether the magnitude is greater or smaller. In case of threshold and linking, we look into the normal direction of the gradient and then we see whether this pixel is connected or not connected, and we can connect it if there are some stronger values in that direction. And similarly the thresholding, it's like dropping the weak edges or no edges, pixels with no edges. So another example, effect of sigma. One thing is important. I described Sobel as derivative, which is in fact which includes smoothing and derivative as well, but that's not the only operator that you have to use. So we can use some bigger operators like Laplacian of Gaussian operators with different values of sigma. Like we have sigma equal to 1, we got these results. Then sigma equal to 2 mean more smoothing, we got these results. It's like better results. So there is no hard and fast rule what value of sigma would be better for one image. So that is like purely the content and the details of an image. Some images are very clutterous, so you need higher sigma. Some images are very sharp edges and no clutter, or no smaller objects, or no objects of interest. I mean, no objects where we do not have any interest, and then smaller sigma is better. So we can say that large sigma detects large scale edges and small sigma detects fine features, like smaller edges are small objects. Let us discuss some applications. Like we have some random objects placed on some surface. We can detect objects in robotics, like in case of conveyor belt. If we have a robotic arm and a conveyor belt, and robotic arm requires to pick some specific elements or objects, then we can develop some image processing techniques. Then we can detect at least objects of some certain feature, certain size and shape. Detection or recognition of coins. Here is an important application. The Canny detector is used on the front view camera of driverless car. So that's the front view of the driverless car, and that's the Canny detector. So Canny detector can help in finding the lanes of any road. So Canny detector in fact helps in finding the edges. Then we can develop over Canny detector, like this one. It's a Hough transform. Hough transform in fact develops or can detect straight lines or lines from image. So we can detect lane from the front view of the camera autonomously. So the basic algorithm is Canny detector. First you have to apply Canny detector to enhance edges, then use Hough transform. Though Hough transform is not the part of this course and is beyond the scope of this course, we will discuss Hough transform in computer vision course, and similarly some other algorithms. But Hough transform in fact helps in detecting geometrical shapes like line, circle, and so on, ellipse. So we can draw lines. Even we can detect whether the line is dashed line or a solid line. So we can make an idea whether the car is moving in the central lane or a side lane. And we can even detect the yellow lines, which are standard marks used on the roads. Here is another example application. It's called corner detection. We can detect corners just after detection, Canny detection. Applying Canny detection, then we have another algorithm which we will be discussing in our next lecture. Though that algorithm is still not a part of digital image processing, but we will discuss as an example of application. That's corner detection. So after corner detection, we have to develop some more algorithms, like how we can save these corners in memory and how we can interpret these corners to detect images. So definitely the topic is not a part of digital image processing, but however we will discuss this algorithm at least, where we can detect corners, corner of edges. So this is apparent entirely different image, and it's different, but we can match the image in different view, different shades, different location, background. So everything is changed. Even angle of the camera is changed, but it is perfectly matched by after detection of these corners. So how do human perceive boundaries? It's like how do human in fact detect objects. So mostly human perception about boundaries is like within an image there could be either a number between 2 to 30 objects. So the humans in fact recognize objects, not only boundaries but the contents within boundaries. And in case of computer vision or image processing, it is sufficient to have at least boundaries. Though the advanced computer vision algorithm requires the complete image and they learn about even the contents within the boundaries, but still the boundary based object detection is still very valid. So we can develop algorithms to detect or draw boundaries around objects. Here is another example. So the image on the leftmost location is the original image, that's with more details, lesser and lesser details, and then this is the original image, this image with almost all details, and then with lesser details and even lesser details, and so on. So the overall, if we are not interested in background, we are interested in only elephants, then this is the perfect boundary, and this is the perfect boundary of elephants. So it's all about foreground and background. So object of interest and the background. Some more images like this one with more details and this one with lesser details, and similarly just one deer and then more details and lesser details, and so on. Some other examples. So here is some images with human mark boundaries. So the darker pixels are darker where more humans mark the boundary, and a lighter pixel mean lesser number of persons mark these boundaries. So that's purely human perception or human perception of boundaries. Here is the Canny versus human. So boundaries are detected using based on Canny, and then colors, then texture, then combining Canny, color and texture we got these images. And the human perception of detecting boundaries is still better than this, though this combined boundary detection is very good, and we can use this concept in computer vision, object recognition, autonomous recognition of objects like faces and so on. Here's the zoomed in images. So the boundaries are edges detected by Canny, and then boundaries drawn by humans are perceived by humans. So you can see most of the time Canny in fact not only preserving the edges but also the contents within the image, like this one, where human perception is sometimes human perception is very raw, very generalized, like in this case. Canny has, though the boundaries are not sharper, but Canny has preserved more details, like over here, in comparison with the human perception of boundaries. So these are the references. Let's stop this video over here. See you in the next video. We will be discussing the last topic related to edge detection and gradient, Laplacian gradient, and then Canny edge detector. That's in fact about corner detection, though not a topic of image processing, but will be discussed as an example, as an application of edge detection. So see you in next lecture. Goodbye.